facilities in India. You're on, Arun.
Thanks. Yeah, sorry I couldn't be there personally. Thanks a lot for the invite. I'd been a bit unwell, and that's why I had to skip coming to Bangalore. I hope the talk can still be effective. Thankfully, I can see all of you. So the first talk is just a factual talk. This is a list of observational facilities that exist in the country. Across various institutes. These are almost all of these are national facilities or accessible to everyone in the country. So if you want a very short version, now I know the audience is a mix of some conventional astronomers, some gravitational wave astronomers, and some people from statistics backgrounds. So I'm trying to keep the slides as general as possible, but this is a summary of what we have in the country. These are all the observational facilities that exist or are coming up in near term. We have in red here are various optical and infrared ground-based telescopes. In green are the radio facilities that we have, and in purple here, of course, not based really in Afghanistan, is Astrosat. I had no idea how to show a space telescope on a ground-based map. So if we look at the optical infrared facilities first, these are the major ones that are active. We have the 2-meter telescopes from IIA and IUCAA, the infrared telescope at Mount Abu from PRL, and the very newly commissioned 3.6 meter, which is now again Asia's largest telescope. So let's start with Hanle, the Himalayan Chandra telescope. This is a 2-meter telescope. If my mouse is visible, this telescope dome is seen just below the HC of the HCT here. This is a beautiful site in Ladakh, in the Himalayas. The telescope is at an extremely high altitude. This is 4.5 kilometers above sea level, one of the best sites around the world for infrared. And the reason for that is that Ladakh is a very high desert. So the water vapor content in the sky is very low. And that makes it really good for, that gives it really good transparency for infrared observations. Of course, the prime instruments here are not infrared, they're optical. The site has about 260 clear nights per year. That's pretty good by global standards. The median seeing is also about an arc second or lower. And because this site is so remote, actually the observers usually don't go to this site actually. They observe from a site just outside Bangalore. It is controlled from the Hoskote campus of the Indian Institute of Astrophysics. As far as instruments are concerned, it has a standard suite of instruments. It switches between what is called a FOSC, the iFOSC. This is the faint object spectroscopic camera. And it also has an infrared imager which is available on certain nights. So several of the instruments can actually be mounted together on an instrument cube, which is shown in this image over here. So you can actually mount 4 instruments together and swap between them in real time, which is excellent if you want to switch from one kind of observations to another. If you want to do, say, photometric observations of some transient which is fading away, but then you find in your first images that it is bright enough so you actually can take spectra for it and so on. This is not quite true when you're switching to the infrared instruments, because infrared instruments need liquid nitrogen to be pumped in and maintained at cryogenic temperatures and so on. So that those switches need to be done in daytime. After HCT, a very similar setup is actually the IUCAA Girawali Observatory, IGO. This is also a 2-meter telescope. This is located in central India, just off Pune. And this site is a bit worse off. The site was selected to have more easy access for students and other astronomers to get trained on it. So this has about 180 clear nights per year. But in July to October in the monsoons, the dome is actually sealed shut, and they put in dehumidifiers inside the dome to make sure that the telescope does not get damaged by the highly humid weather. But again, a similar suite of instruments. We really like our iFOSC cameras, the faint object spectroscopic cameras. So Hanle has it, IUCAA has it, and will soon come to the 3.6 meter, which also has the same. Both these telescopes we have actually used for various transient follow-ups, including some follow-up for gravitational wave sources that have been reported by the LIGO collaboration. Um, Going a bit outside India, this is the South African Large Telescope. This is a 10-meter telescope in South Africa. And the reason this is listed here is that while this is strictly not an Indian facility, India is a 10% partner in this. Just as India is now a 10% partner in TMT. And SALT comes with the standard suite of instruments that you would expect from any very large telescope. So it has optical cameras, a few infrared instruments, optical spectrographs. It has a high-speed imaging camera, and so on. Coming back to the mainland, this is now the 3.6 meter Devasthal optical telescope. This image is about 3 years old. You can see that the dome is actually being built, but the telescope is now fully functional. The first round of proposals was due earlier this month, and we expect time allotment to happen sometime soon. And this telescope now is Asia's largest optical telescope. It's a 3.6 meter active mirror with a default spot size of half an arcsecond, which means that you're limited by sight seeing, which sight surveys have showed as better than an arcsecond. It also has by design a 30 arc-minute field of view, which is pretty wide for such a large telescope. It was built in partnership with Belgium. There's a Belgian company called AMOS, which made the telescope itself. And the first round of observing, about 1/3 of the time was reserved for Ares, which is the parent institute for this telescope, 7% for Belgium, and about 60% is the Indian open time available for any astronomer in the country. The primary instruments which were available right now for the first observing call were 4K by 4K, so a wide field optical camera, then again a FOSC, a faint object spectroscopic camera, and TIFR has also built what they have called TIRCAM2, the TIFR infrared camera. Coming soon, there's a set of other instruments. So apart from the spectrograph, which I mentioned, which will have about a spectrograph and imager, which I mentioned, which will have about a 1/4 degree field of view, and the optical imager, which is already present. There's also going to be another spectrograph in the near infrared. They are also working on a high resolution spectrograph, which will allow us to do more detailed studies for ranging from chemical compositions to radial velocities. And there's a especially cool instrument being built at IUCAA called, which is a deployable IFU. So the idea is IFU is something called the integral field unit. So you have a set of optical fibers which allow you to take spectra of a 2D region on the sky, so that you can actually, say, study kinematics of a galaxy or composition of different parts of the galaxy. And what is nice about this one is that instead of having one IFU, this will have some 6 or 8 integral field units, so that in a single field of view, you can simultaneously study 6 or 8 galaxies in a single shot. The next one in the line is again at Devasthal. This is a smaller telescope, 1.3 meters, called the Devasthal Fast Optical Telescope. So here's the telescope itself, and it's mounted in a shed which is raised above the ground. The idea is that when you roll off the entire dome, the shed actually comes into equilibrium very quickly with, so this entire brown roof that you see here can be rolled off. So it comes into equilibrium with the environment very quickly, and that allows you to get excellent observing conditions. So right now this has a small camera on it, but the plan is that when an advanced camera is built for the 3.6 meter telescope, its existing 4K camera will be moved to this telescope, and that will be a very good investment because by design this telescope is a wide field telescope, a capability which is not being utilized at this point due to limitations in the camera. Wide field cameras are extremely expensive. But if this is actually used as a wide field telescope, it will be excellent to do transient studies. For example, again with LIGO, where you have extremely large areas of the sky that need to be imaged when you are searching for a transient. Finally, among optical and infrared, I'll talk about the infrared telescope at Mount Abu. This is a 1.2 meter telescope, And at the same site, they're also now building a 2.5 meter telescope, which should be up in a few years. So this one is different from the rest of the facilities in the sense that this is dedicatedly used for infrared studies. They do have some optical instruments, but they have a good slew of infrared instruments, which have been put to use a lot in studying, for example, novae and some supernovae. So this one is located at about 1700 meters above the ground, above the sea level, sorry. And it gets a good amount of clear nights through the year. And the main instruments, as I already mentioned, are the infrared instruments. Now from optical, I'm moving to radio. This is the Giant Meterwave Radio Telescope, or the GMRT. This is again located off Pune, not very far from the IUCAA Girawali telescope. GMRT consists of about 30 dishes, each of which are 45 meters in diameter. And they currently work in 5 bands, going from 150 megahertz to about 1.5 gigahertz. And there's a major upgrade underway. A lot of the work has already been done to upgrade this so that you will have continuous coverage all the way from about 250 megahertz to 1.5 gigahertz. Currently, before LOFAR, this is the largest low frequency array in the world that exists, the most sensitive one. Individual dishes nicely can have a 1 square degree field of view. It depends a bit on what frequency you are observing. And the design is that the dishes are spread over a Y-shaped array, which gives you high angular resolution. The diameter of this array is about 25 kilometers. But there's a bunch of dishes that are concentrated in the central square, which gives you good coverage for getting fluxes of radio sources. Finally, I'm coming to Astrosat. So Astrosat was launched about a year and a half ago. This is the first Indian observatory class satellite. It's a multi-wavelength satellite. It has 5 instruments on it. 4 of them are co-pointed. There's a UV and optical imaging telescope, ultraviolet and optical. 2 tubes which are located in the center. There's a soft X-ray focusing telescope, which is very similar to the XRT on Swift, if some of you know what that is. Then there is a large area X-ray proportional counter, which are these 3 large boxes that you see along the sides of the satellite. This is the world's most sensitive X-ray timing instrument. It is a lot more sensitive than RXT, PCA when it was at its full sensitivity. So this has been a huge leap for X-ray timing studies. The 4th co-pointed instrument is this cadmium zinc telluride imager. You will hear a bit more about some of these instruments in the next talk. And then finally, apart from these 4 co-pointed instruments, at the side here we have a scanning sky monitor. This consists of 3 slits, which each of which have a roughly 100 square degree field of view, and it rotates perpendicular to the satellite so that it can cover up to about 50 to 80% of the sky in a single orbit. And that is used for monitoring all the X-ray sources, all the bright X-ray sources in the sky to see if any one of them has undergone outbursts. Here is the field of views of the co-pointed instruments. So the yellow box is the largest field of view, about 4.5 degrees on a side. That is the cadmium zinc telluride imager. Then at the center, the red one is the LAX-PC field of view. And within those are the SXT and UVIT field of view. So for roughly a central half-degree region, you can get coverage from all 4 telescopes. And as you go further and further off axis, you lose coverage from some of the instruments. What do all of these instruments do? Well, each of them covers a slightly different wavelength range. And you may want to think of it in terms of wavelength or frequency, or if you want energy, like X-ray astronomers usually would prefer. Or you can even think of it as the effective temperature of what instrument, what object is going to emit at that. And on these scales, CZTI, LAX-PC and SXT cover the X-ray band going from less than 1 keV to about 200 keV. And then there's a small gap in what you would call very soft X-rays or very far ultraviolet. And then the UV and optical imaging telescope actually gives you coverage in near UV, far UV and optical. So this is Astrosat, and I'll end with this. I'll leave a map of all the observatories and their locations on screen again, and we can take any questions. Excuse me.
Questions for Varun? Actually, I will kickstart with this. So, Varun, for this Mount Abu telescope, what is the field of view? 1.2 meters.
For the infrared telescope, that's about, it depends a bit on the instrument, but it ranges from about 6 arc minutes to about 10 arc minutes.
Okay, it's not quite a transient class telescope then, for gravitational.
So if you want to use, okay, so for gravitational wave perspective, the only telescope I think which could really be used are the 1.3 meter telescopes at Kavaluru, which I didn't talk about, or the Devasthal 1.3 meter telescope. In the next talk, I'll also talk about a smaller telescope that we are deploying soon, later this year in Ladakh. These are the only instruments in the country which are wide field enough to do a blind search for LIGO counterparts. However, what is happening more and more often within the EM follow community around LIGO is that people are focusing more and more on the use of galaxy catalogs for actually searching for counterparts. So what you do is even the low latency information that one gets from LIGO now actually has some volume information. So for each direction in the sky, you have some idea of how far the source is likely to be. And people combine that information with pre-existing catalogs of galaxies, and they use that to target specific galaxies. So you weigh the probability, the LIGO probability distribution by the masses of the galaxies in some sense, and that tells you how likely each galaxy is to contain the true LIGO counterpart. And there have been some older studies which say that if you, even if you do say the top 10 or 20 galaxies, you actually have close to 50% chance in some cases of finding the electromagnetic counterpart. So then you don't need a telescope which is as wide field. You just have to have a few arc minute field of view so that the entire galaxy will fit in that. And there we could use any of the telescopes in the country. That said, the only telescopes which have MOUs with LIGO just now are IUCAA's Girawali telescope. That's it. And through partnerships with IUCAA, we have been using the Hanle telescope for some follow-up.
So I understand that this new Devasthal telescope would take some load from this 2-meter class telescope, right? This wide field telescope. So is there a plan to use it for transient studies in the future?
Hanle already, the 2-meter telescope at Hanle is already being used for transient studies even now. It will take a couple of years before the 3.6 meter is functioning very smoothly. And then we hope that it will free up more time on other telescopes so that we could use them. We could get a larger fraction of the time for transient follow-up. But that is more a policy question than a technical question, and I'm not sure which way the policy will go.
I would just like to add here that a lot of it will also depend on the brightness of the source. Because if something can be done with a 2-meter class telescope, we may not necessarily need a 4-meter class. But for fainter sources, certainly the plan is to use the 4-meter class telescope. Mainly for, which one? That's those are 1-meter class. And we don't have a spectrograph on that. So for spectroscopy, we are certainly relying on the 2-meter HCT and the 3.6 meter. But yeah, follow up with the larger telescopes, yeah. But it will not be very easy to slew a 4-meter immediately for any transient studies, but for a follow-up spectroscopic observation, it will certainly be used.
Varun, I'm going to raise a point during the panel discussion, but I might as well ask you right now. What about the automation of various Indian telescopes? Where do you see that going? When do you think that's likely to happen, and how?
That's a sensitive question. Again, the reasons are not technical. It is more a policy issue. We had a series of discussions about this a couple of years ago among various institutes. in principle, people do agree that automation would help build the efficiency of the telescopes, and this is especially true for the meter class imaging only telescopes. But it has to be a policy decision by the institute, and some resources have to be allotted. Um, we have done proof of concepts here already. We have at IUCAA we had developed some techniques which my students are improving further now for automating telescopes and automating even the default data processing, so that astronomers can work with higher efficiency and focus more on the science. But I think this has to come as a policy directive from the concerned institute saying we want to automate this telescope. Also, for spectroscopic observations and instruments with or telescopes with more complicated instruments, automation is not that straightforward. So I don't expect the 3.6 meter or the Hanley 2 meter telescope to be automated anytime soon, because if I think of myself as an observer using a spectrograph at this telescope, I would rather want to be there and control the settings myself rather than trust an automated script for doing these. But for photometric telescopes, technologically it is straightforward. There has to be a policy decision to enable it.
Varun, I just wanted to add some things about the three green hexagons which you have put there. So GMRT, just for the audience, so GMRT has proposal which is right now in an advanced stage for what is known as commensal observing. So in this commensal observing mode, wherever GMRT is looking at, whatever it is doing, there will be a low frequency commensal backend which will all the time be sort of running. How it will work and so on, as Varun said, is also still a matter of policy decision. But there is a proposal for doing this, and hopefully in a couple of years that should be online. So at least part of the sky, and low frequency you have a fairly wide coverage. So part of the sky all the time is being observed by GMRT. So that's one thing which I wanted to mention. Varun didn't mention ORT. So ORT has undergone an upgrade. It is now called as, the upgrade system is called as ORT Wide Field Array. So ORT, just for everybody's information, is actually a telescope which is an array of 1054 dipoles. And each dipole covers a huge part of the sky. So in the previous avatar, ORT used to have a very narrow field of view. But in the wide field array, each dipole is separately correlated. So you could, in principle, have a fairly large sky coverage at 325 megahertz. So, so that also would be sort of running and would also be useful for follow-up. Gauri Badnoor, the third thing which he had lifted there is actually a wide field instrument. And but it operates in fits and sort of those things. But with an effort, probably that could also be very useful for electromagnetic follow-up. But all this crucially depends on what kind of signal we expect. And like Sukanto was saying, you have to do it within a day or so. So those are the issues.
Not for radio, right?
Yeah.
Radio apparently peaks at months after the event.
Your plot said 10 to the power 6 seconds. So I took that. Yeah.
Peaks to months, yeah.
So if it is exactly like GRBs, then this is also it depends on the frequency evolution of the emission which is there. So because most of the frequencies which I talked about are between 30 megahertz to something like 600 megahertz. So what kind of signal you would get there, it depends on that. But if you have a good possibility there, these instruments are also going to be very useful in electromagnetic follow-up.
Sensitivity? What will be the sensitivity of the Gauri Badnoor and ORT?
Of ORT? Well, I don't have a number off the top of my head, but the sensitivity is exactly, so the collecting area is about 4,000 square meters. The same collecting area would be there because you are forming multiple beams. So what is being done is that you are using 1054 dipoles to cover the entire field of view in multiple beams. Not all of this is implemented as of now, but it is in an advanced stage of implementation, and hopefully in a couple of years should be available.
BCJ, what is the field of view of the advanced ORT? Total field of view?
It's in tens of square. See, it's of the order of 50 to 60 degree if you take individual dipoles. But right now we don't have that possibility. We are combining few dipoles. So it is currently of the order of few tens of degrees, maybe 10 to 15 degree and so on. But eventually there is a plan to go to individual dipole digitization. That digitization is done, but the correlation is not yet there. Okay. So in principle, it can have a full sky, almost full sky kind of coverage.
Okay. Thank you.
Any other questions or comments for Varun? Okay. Thank you, Varun. So let's go to your second talk on